Right? And what I want you to remember throughout is that because we're now working in 2 dimensions, we have to work with vectors throughout. And we said, if I've got 2 vectors, let's say this is a vector B and this is a vector A, then if I draw in a vector over there from A to B, that vector is vector B minus vector A. Right, so that's the one picture, so that's how we subtract vectors. If you can just keep that picture in your mind. And then the other one was how we add vectors together. We said, let's say if I've got a vector A and I've got a vector B, then if I want to add them together, their sum is given by this vector. A plus B will be that vector. So subtraction and addition of vectors illustrated graphically. Then we said, well, let's take any old example. Let's say we've got an acceleration vector that is equals to some sort of acceleration along x and no acceleration along y. So if I want to draw this, and if I set up an xy axis that it's always like this, it means my acceleration vector will look something like that. It's a vector pointing in the same direction as x. And let's say I've got some initial velocity vector that is equals to some sort of initial velocity along x plus some sort of initial velocity along y. So my velocity vector, it has got some component along x and some component along y. So I would be able to draw it, say, like this, where the 2 components, that would be v initial x, that would be v initial y, and this is my initial velocity vector. And now we can start to play around. We're now working in 2 dimensions. My acceleration points along the x-axis, my velocity points in some arbitrary direction. If I now want to figure out, for example, how will my velocity change, because I've got an acceleration. Acceleration means velocity has to change with time. So how can we do this? Well, we have a hint. Remember, we derived this equation at some point. We said final velocity is equals to initial velocity times acceleration times delta t. Now we derived this for constant acceleration in a straight line, but let's for now write this as vectors. If I look at this, it means my final velocity is my initial velocity plus the acceleration vector times time. So if I look at my picture, how do I add together vectors? It says, okay, let's take my initial velocity. There we've got that. Add to it my acceleration times time, so it might mean the acceleration vector is now slightly lengthened because I'm multiplying it with some certain amount of time. And I know immediately my resultant vector, so the sum of these 2 is given by, if I take the tip of that vector and join it, or the tail of this vector and join it to the tip of that vector, then this has to be my final velocity according to this sum. Now if we look at this on a y-axis and an x-axis, what we see is that the y component of the velocity remains constant. The acceleration, because the acceleration in this case, we assumed it's pointing in x, it did not change the y component of my velocity. The initial velocity and the final velocity have both got the same y component. However, the initial velocity had that x component, and the final velocity has got a larger x component. So what we see here is, if I've only got acceleration in one direction, I only change the component of the velocity in that same direction. So if I've only got acceleration along x, I only change the velocity in the x direction. So I'm only increasing one component of the velocity. And if we had an acceleration along y, we would only be changing the y component. More generally, if we've got acceleration along x and y, we can use this equation to split the problem up into an x component and a y component, figure the two out separately, join them again together with time. And that's what we're going to do in a second. Right, so this is the general idea behind two-dimensional motion. And the first problem we're going to look at